In this video, our main topic is the Kolmogorov backward equation. It is a partial differential equation that describes how conditional expectations evolve over time. The famous Black-Scholes equation in mathematical finance is a special case of the Kolmogorov backward equation, based on the geometric Brownian motion and option pricing. So before deriving the equation itself, let's first understand the setup of the problem using the example of the option pricing. So we start with the stochastic process. This is the most general form. It is also known as the Ito process. In the case of the option pricing problem, we already defined the geometric Brownian motion to model the stock price. So the quantity that we are interested in is a conditional expectation of the stochastic process. So one way to think of this conditional expectation is that, let's say that we are starting at time t at position x. Then according to this stochastic differential equation, we can just evolve this process into different paths. So the quantity that we are interested in is at the time capital T. So the process value at the capital T is random, right? Basically, this xt is a random variable. And we are interested in the expectation of some function whose value is depending on the process value xt. For example, this function can be the option price, the call option price, and that can be written as xt minus k positive. So this is how we define the function at time capital T for the option price. In the Kolmogorov backward equation, we are interested in the time evolution of this conditional expectation. And if we look at this equation here, we have the partial derivative of v with respect to time, and that equals to something related to the first and the second derivative of the position. And now, just to clear up the concept, we have actually talked about this before. The conditional expectation is a very interesting quantity. The interesting thing is that this expectation is not random if our initial value is provided. This is because if we start from this position, the density function at time capital T is fixed. Therefore, the expectation is also a fixed quantity. But we must be careful, because sometimes people write the conditional expectation as the expected value of v at time capital T xt given capital Xt. So notice that we are conditioned on a random variable here. So the thing is that if this capital Xt is denoting a random variable, then this conditional expectation is random. Okay, so let me give you an example with the option pricing to consolidate this idea. Okay, so let's consider this example with random stock price. So let's say that the stock price today is $100. And let's say that I bought a call option today to bet on the stock price after a week at day 7. The fair price of the option is the average payoff depending on the stock price after a week, which means that the option price today and our starting point is $100. That is the expectation of the option payoff at day 7, but the stock price is random, so we denote that as x capital T. And in here, we actually don't need to consider the conditional expectation. We can just write the ordinary expectation. So this price is not random. Okay, now for the conditional expectation, let's think about this case. So the question we want to ask is, what is the option price tomorrow? Now that's where the conditional expectation come in, because we don't know the stock price tomorrow. And we know that the option price depends on the stock price. And we can still write the option price in this way. So we are interested in tomorrow's option price, so t equals to 1. But now we don't know the stock price, so we use a placeholder x 1. So that equals to the expectation of the option price at day 7. The stock price at day 7 is still unknown. Now we need to condition this option price based on tomorrow's stock price. Now this quantity is random when we don't know the stock price tomorrow. But this value will become fixed after we obtain the stock price tomorrow. So it's not random. For example, the stock price tomorrow is $105. So the reason is that suppose that tomorrow's price is $105, then we just basically regenerate the path, right? You can use the same stochastic process to regenerate the path starting from this position. And the expectation at day 7 is not going to be random. So this is very important to understand the Kolmogorov backward equation. So as for the notation of this video, when I write equations such as v conditional x t equals to small x, or when I write the expectation of v conditional small x, so those conditional expectations are not random. It is the expectation given a fixed value. So this is in contrast to the case where it's conditioned on the capital X. Okay, now we are ready to dive in the derivation for the Kolmogorov backward equation. Oh, there's one more thing. Let's do a comparison with the Fokker-Planck equation first. Because the Fokker-Planck equation we derived last time is also known as the Kolmogorov forward equation. So just recall how we derived the forward equation. So we basically start from a transition rule. From t to t plus delta t. And then we apply the Taylor expansion to basically approximate the transition probability, the probability function, based on the change of the position. And then we use some algebra to just reduce that to the moment. And from that, we can derive the PDE. So that is the strategy here. The same strategy can be applied to derive the backward equation as well. But we need a new transition rule. So this rule is known as the iterative expectation. Okay, so let me just write down the rule first, and then I'll explain what it means later. Okay, so this is the equation. So if we look at this equation here, right, So on the left-hand side, we have a random variable whose randomness depends on x capital T. So this is just equivalent to we starting at the time 0, and then we are computing the expectation of some function at time capital T. So the iterative expectation is saying that we can break it down into two expectations. We can just split the time period into two parts. Let's call this split point as small t. So it just means that we find the expectation at the time small t first, and that is a random variable depend on x small t. Then we take the expectation again. So in the case of option pricing, it just means that the option price today let's say that the stock price is at $100. That equals to the average option price. Let's say that the option price at, let's say, it can be any future time, but let's just say it's tomorrow. Because we don't know tomorrow's stock price, the option price is random. So that's why we need to take the expectation of it, and that equals to the option price today. So this iterative expectation is not that difficult to derive as well. We can actually derive it just by expanding it into the integral. So on the left-hand side, you have the integral of v, then we have capital T, and say, let's say that the x capital T equals to little x times the conditional probability times the probability density given by capital T, and then basically a transition from, let's say we start from time 0, and then the initial value being x0, where we just integrate over dx. So the key idea is that we can just break down the probability function, right? Break down the transition probability function. Let's say we have some middle point, small t, at value y, times the transition from 0, x0, to y. Then we just need to integrate over the state dy. Okay, so this is just the Chapman-Kolmogorov equation. And then we can just move the terms a little bit, right? So the idea is that we can combine this v term here with this probability, right? So that will just give us the expectation. So let me write that as the probability of ty 0, x0, and then we have another integral of v times probability of tx then we'll first integrate over dx, then integrate over dy. Now you'll see that this is just an expectation. So this equals to the expectation of v given xt equals to y. Then basically we have the integral as the probability density times something, right? So that is another expectation. So this equals to the expectation of V. Right now, see, this is just the right-hand side, right? We derived the iterative expectation rule. Okay, so now we are really ready to derive the Kolmogorov backward equation, finally. So the idea is that we just compare the expected value between t and t plus delta t using this iterative expectation. So let me write it out. Okay, so basically we start with the iterative expectation. Okay, so now we can just replace the expectation with the function v that we defined. So on the left-hand side, what we'll have is just v of t and x. So that equals to the expectation of v at t plus delta t. And then we'll have a random variable here, right, as x capital T plus delta t given xt equals to x. So the idea here is that we can just write the right-hand side into an integral. And let's just consider that the change of time from t to t plus delta t, the position changed by the amount z. So the x, and that becomes x plus z. Okay, then we can just expand this integral, right? The integral of v at t plus delta t, and the position becomes x plus z times the transition probability. And then we just need to integrate over z. Okay, this is a nice formula, right? Now we just need to think about how we apply the Taylor expansion on it. So we're just gonna use a two-dimensional Taylor expansion. So that's just gonna, so we can just say that v t plus delta t x plus z. So that equals to v of t and x plus the first order change as partial v partial t delta t plus partial v partial x times z plus. So for the second order term, because we already learned Ito calculus, so we know that only the position matters for the second order. So I'm not going to write the delta t term. I'm just going to write the one with respect to the position plus all the other terms. Now we can just plug in this equation into the integral. And then we just separate out the terms directly. So we'll have v t and x times p. Okay, and for the simplicity, I'm just not gonna write out all the arguments inside p. We know that it's a transition probability. Now this integrals looks very familiar, right? We see this many times throughout the series. They are just the moments for the random variable z, the jump of the position, right? So first, let's just look at one thing at a time, right? So the first one, so this just equals to 1. And all we left for this term, it's just going to be v of t and x. And then the same for the second term. So we're just going to have partial v over partial t. And then for the third term, right, so that is just the expectation for z. So this equals to expectation of z. So remember our process, we have the change of xt equals to the mu times dt plus sigma times dbt, right? So here we can replace this dxt with z. Okay, I should say that z equals to delta xt, right? Just to be safe. So this means that the expectation of z equals to mu txt delta t, and then the second moment of z equals to the variance of z plus the expectation of z square. So this term will be killed because it has a delta t square, right? So the variance of z is just going to be sigma square times delta t. Okay, so now we can just replace the integral with moments. So that's going to give us partial v partial x, and then we have mu of t and x times delta t plus a half times the second partial sigma square t and x delta t. And for the left-hand side, right, we have the v, t, and x. Okay, so I think that I missed a delta t in here, right? Because if you look at the Taylor expansion, right, we have the delta t association that I forgot to add. So now all we need to do is just to move the term a little bit, we'll reach the Kolmogorov backward equation, right? So we see that these two can cancel out, and then we can just divide that by delta t. So in the end, we'll have partial v with partial t plus partial v with partial x times mu plus a half the second partial times sigma square equals to 0. This is a Kolmogorov backward equation. So basically, this equation tells us the time evolution of the conditional expectation. And finally, let's just look at one example to see how the Black-Scholes equation is a special case of it. So for the Black-Scholes equation, the stochastic process is given by this. It's given by the geometric Brownian motion. So all we need to do is just to replace the mu and sigma with this. Okay, so we'll have partial v partial t plus partial v partial x times mu times x plus a half the second order derivative times sigma square x square equals to 0. So that is the Black-Scholes equation for option pricing. So if you compare to the common Black-Scholes equation, this is a one without the interest rate. And for the equation that has the interest rate in it, we're just going to define the function v a little differently. So this is how we define it, right? We can define the function v equals to e to the r, so r is the interest rate, times capital T minus small t times u. So basically the idea is that our option price today equals to the expectation of future payoff. And we need to multiply that by a discount factor. So a very quick and dirty way to think about it is just inflation. So for example, the future payoff, the expected payoff is $100 in a year. So the finance people saying that the future $100 does not equal to $100 today. If we account for the inflation, maybe that's only equals to $90. So that's why we need to multiply this discount factor given by this exponential in here. Now, in order to reach the most common form for the Black-Scholes equation, we just need to replace v with this function. So we just need to compute the partial derivative of it, right? So let's just do that real quick. So partial v with partial t will just equals to e. So we need to use the product rule times partial u partial t plus, or it's minus r times e to the rt minus t times u, and then partial v with partial x just equals to e to the r partial u partial x, and then the second derivative equals to times the partial square u partial x square. Okay, so now if we plug into this equation, right, we see that the factor can be cancelled. We see that this discount factor can be just cancelled. So what we will left will just be the partial u over partial t minus r times u plus partial u partial x times mu times x plus a half the second derivative of u times sigma square x square equals to 0. Yeah, so this is a common form for the Black-Scholes equation. And I think there's one more nuance, is that in the option pricing, right, we use the interest rate to replace this factor mu in here as a drift. So that has to do with the risk neutral pricing. So this is a little bit out of scope for the series, but if you are interested in that, you can check it out. Okay, so that's pretty much about this video. We started from conditional expectation and arrived at a partial differential equation. Now, interestingly, the Fokker-Planck equation is also called the Kolmogorov forward equation, and it is very closely related to the backward equation. Even from the derivation, you can already see the similarities. Both equations ultimately coming from the same transition structure encoded by the Chapman-Kolmogorov equation. So the difference is really about what evolves. The forward equation evolves probability density, whereas the backward equation evolves the expectation. In fact, these two equations are due to each other and are connected through the adjoint operators. And this is something we're going to look at in the next video.